And the idea for you is to talk about the science of earthquakes, how we understand how they work, with application to Italy, and then try to talk about some of the broader impacts. So even here you can see, like, what are those white things in this picture? Cheese. What kind of cheese? Parmesan, right? So this was an earthquake that happened in 2012 in eastern Italy in the area of Parma. And it was only like a magnitude 5.6 or 5.8. It wasn't a huge earthquake, but because of where it occurred, it had a very specific and focused impact on one industry, which was that it really affected the cheese industry for some time. So just like the Napa earthquake in California ruined like $100 million worth of wine, sometimes earthquakes, even though they're kind of small, can have important impacts. And for Italy, for example, you guys know about the kind of cultural resources which are really widely appreciated and deeply valued for Italy. And it can be buildings, but also could be something like a cheese industry. So let's talk about all this. So the idea is a little bit of geology, like why are there earthquakes in Italy? And then what are some of the earthquakes there? And then we'll review several historic ones and then kind of run out of time, basically. So I'll go as far as I can. So here, the story of Italy is kind of like a dance between Europe and Africa. And so if you look in these figures, these are different views of the world now. And so it shows the land masses and the bathymetry, the seafloor. You can see so much about plate tectonics on the seafloor. It's amazing. But basically, if we look at the upper part, you see Africa and Eurasia, with Italy kind of right in the upper middle. And we know other things have happened, like you can see over here in the lower right, you see India has slammed into southern Eurasia to build the Himalayas and Tibet. So that's really a sort of vigorous continental interaction that built the Himalayas. But the interaction between Africa and Eurasia is a little bit more delicate, but it still has driven some significant deformation. So let's go back in time. So just watch carefully. So this is 20 million years ago. So what's different? Can you guys see? Sorry, going wrong. So it's 20 million and then 35 million. So let's start 35 million years ago. Looks to me like the Mediterranean is a little bit wider, has some shallow margins, so it's probably a little bit warmer on the Earth at that time as well, so sea level was a little bit higher. But you also see the assembly of Eurasia is not complete, so that whole southern zone, like this whole zone here, India has not yet collided yet with over in the east, and the whole zone, like where Turkey is and what we'd say Eastern Europe now, there's a lot of these smaller pieces of land masses separated with oceans, right, or seas, small oceanic zones. But then if we go 20 million years ago, so 15 million years, we see Africa rotates a little bit. India has kind of completed its initial contact with southern Eurasia, and we've sort of built the Mediterranean. But the key thing to look for is we started making the Alps. It's kind of small, but you see that little arc right there. Basically, that's Italy climbing into southern Eurasia. And we call Italy, sometimes it's, when we talk about this sort of a microplate, we say Apulia. So Apulia has slammed into southern Eurasia and starts building the Alps 20 million years ago. And so then when we get to the present, we've sort of completed that collision, and actually you can see that Africa is starting to pull back. So look, 20 million years ago, we didn't really have the Red Sea and the Gulf of Aden weren't really well developed. They were just starting to rift, but we hadn't built a seafloor there yet, whereas now we see that extension happening. So as I said, the interaction between Africa and Eurasia is really complicated, and it's kind of coming forward, and Apulia is sort of sitting in the middle, comes together, but then it starts sliding back. But what that means for Apulia, for Italy, is a very complex pattern of deformation. So let's just look, if we now look at the kind of major fault systems of the region. But when we come then into the Apennine, or the mountains that are the backbone of Italy, we see there's kind of a big fault zone in the middle there that was really formed a little bit earlier in that convergence time, and now we're starting to pull the center part of Italy apart. But we still see some zones of major convergence, like the Alps and the Carpathians, still show that shortening. So now let's look at earthquakes. So basically all this plate tectonic motion is kind of like the engine that drives the earthquake. So it's sort of pushing or pulling, and the earthquakes are the steps of deformation that accommodate that stretching or pushing. And so also what I just showed you is kind of millions of years of time of deformation, but we can see it even in the snapshot of like the last 50 years or so. And the reason why we usually look at the last 50 years is because that's the time period of the development of seismic networks that lets us measure earthquake locations and magnitude, which really didn't go until the 1960s, largely initiated by nuclear test ban verification. So it's easy to see if somebody fires off a nuclear weapon if you have a big seismic network, but also a nuclear weapon is kind of like a small earthquake. So anyway, the side effect of all that monitoring was to build these great catalogs of earthquakes for the world. And what you can see here is as Italy is under these earthquakes, the kind of size and color goes with the magnitude. And you see actually Western Turkey is full of earthquakes. We know that from the 1990s, especially, right? In the north was a couple of really big ones. And then also North Africa and southwestern Spain have some earthquakes due to all this motion I've been just talking about. So let's move in then to Italy. And so these black lines are kind of boundaries along which relative motion occurs, like faults. The teeth show particular kind of faulting where the teeth are kind of on the upper side of a zone where the other side's going down. So teeth are on that upper side. So that means there's convergence and like under thrusting where the teeth are. And so we see then, we'll talk about the relative motions. Let's talk about geography. So we have the Alps in the northern part of the system. Po Plain is in the northern part of Italy where Chiara is from, basically, the northern part. And then the backbone of Italy is the Apennine. And then we get down to the heel and to the toe. This is sort of the tail end of the Apennine, and then the toe points into Sicily. And so then if you look at the earthquakes, so on the right side, all the little black dots are just seismicity, just locations. And these beach balls are indications of earthquakes where we kind of can tell the sense of motion in the earthquake. So it's like you're looking at the top of the beach ball, and if the black panel of the beach ball, if it's black, it means it came toward you. And then the white means it goes inward. And so we can see that some of these show, like where the black goes up, it means it's kind of pushing inward and popped up that zone. And where the white is at the top, it means it's stretching. So the middle part dropped down. So what we can see is the central Apennine have a lot of stretching kind of east-west, and the center drops down. And that's actually, those are our star earthquakes, are those ones that we'll talk about. But then down in Sicily, there's kind of a lot of complexity, but some with black, some short. And so here's maybe the most important one in terms of plate tectonics. So if you guys were starting to rest, maybe wake up for a second. So I talked about like, seismology. We can measure earthquakes, but we can also measure the motion of points on the earth using GPS. So just like you come on your phone, you go somewhere. The problem is your phone has what's called single channel GPS. So it only knows where you are to within several meters, which is fine for like navigating. But if you want to study motion of the Earth's surface, you need to get down to millimeter accuracy. So what they do is called differential GPS. So you can kind of correct for a lot of uncertainty by assuming you know where one base station is, and then that the other station kind of moves in symphony with the base. So you can correct out all that apparent motion. So that brings the positional uncertainty down to less than a millimeter. And so what we can see then is that over time we can measure the steady motion of all these points on the ground. So they're almost always like a benchmark. Somebody put some kind of a metal thing in the ground, and we measure the exact, like a little hole in the top of that benchmark. We can go back to it. It's amazing. You can see where it moves. So these arrows, here's the scale. So if the arrow's this long, it's 5 millimeters a year. So it's not very much. 5 millimeters is like half of the tip of your finger, like your fingernail. So it's pretty small, but it's still moving. 10 years, it's 5 centimeters, so it starts to get more interesting. But what we can see then is, think of these also as like cars that are in traffic. And so if the arrows are piling up, it means there's convergence like a traffic jam. But if the arrows are sort of indicating that the one in front is going faster than the one behind, you stretch it out, right? So if you look here, you can see there's pretty long arrows in Sicily, but then as we go into the toe here, the arrows get shorter. So there's a little bit of convergence between Italy and the toe, or between Sicily and the toe of Italy. But the big thing is here in the middle of Italy in the Apennine, you can see this divergence, right? Like the west side's kind of moving northwest, the east side's moving northeast. So that means that basically the Apennine are stretching now. And this is over kind of a decadal time scale. So it's the last, tens of years we can see this, but we assume it's probably longer time scale. And then if the other thing then is, if you go across the Adriatic into the Dinarides, which are the mountains of Croatia, Serbia, Bosnia and Herzegovina, you can see it looks like, although it's not easy to see, but it looks like the Adriatic's getting a little smaller. There's kind of shortening across the Adriatic. So then what all this relative motion does is, again, it's that engine that drives the earthquakes, and the sense of the stretching or shortening tells what kinds of earthquakes. So the interpretation then is on the right. So you see there's this kind of zone of stretching in the Apennine. There's zone of convergence down in the south, north of Italy. There's convergence across I keep saying Italy, north of Sicily. And then there's a convergence across the Adriatic. And a little bit of convergence still across the southern Alps. But the Alps seem like they're mostly dead. They're just kind of popping up more from the recovery of the ice load from 15,000 years ago when last glacial maximum.